In this video, we'll talk a little bit about L'Hopital's rule and indeterminate forms and why we might need L'Hopital's rule. So you may recall when dealing with limits, we sometimes run across situations where we need techniques other than just the standard basic limit laws. So if we say the limit of 2x squared minus 2 over x plus 1, if we try to do the quotient law and the sum and difference law, product law, we would find that this is equal to the limit of 2 times the limit of x squared minus the limit of 2. All of these are as x approaches negative 1. Divided by the limit of x as x approaches negative 1 plus the limit of 1 as x approaches negative 1. Limit of 2, of course, is 2. Limit of x is negative 1, and we're squaring that, minus the limit of 2 is 2, divided by the limit of x is negative 1 plus 1. We would do the arithmetic. We quickly find that we get 0 over 0. Now, the 0 in the denominator tells us really that the quotient law fails. The 0 in the numerator then tells us that there is maybe still some hope that this limit exists. So we do some work, we try something else. So let's rewrite our limit here. So this is the limit to x squared minus 2 over x plus 1 as x approaches negative 1. And one thing that we could try is to factor and maybe cancel some stuff. Notice here that if you look at what we did for the limit in the quotient rule, it's the x plus 1 factor that really creates this 0 in the denominator. So what we would like to do is try to somehow get rid of that x plus 1 factor. So here we factor. So we factor the numerator is 2 times x minus 1 times x plus 1 divided by x plus 1. And now we notice that we can cancel the x plus 1s. And then we're left with the limit of 2 as x approaches negative 1 times the limit of x as x approaches negative 1 minus the limit of 1 as x approaches negative 1. And that would give us 2 times negative 1 minus 1, which would be negative 4. And there our limit does exist, and we have found it by factoring and canceling. Unfortunately, that's not always possible. So suppose that we're given the limit e to the 2x minus 1 over x as x approaches 0. Well, we can quickly see that this denominator will be equal to 0 if we try to do the limit, and so this limit would certainly, the quotient rule would not work. But also, if we do the limit of the numerator, we get 0. So we're in a situation where the quotient rule fails. The numerator is also 0, so that gives us some hope that the limit exists. However, we don't have any way to cancel off this x in the denominator. The e to the 2x minus 1, there's just nothing there to cancel the x off with. So we can't do factoring and canceling. Another trick that sometimes we employ is rationalizing either the numerator and the denominator and then doing some canceling, but nothing there seems to work. So the question here is, how can we eliminate the x to find the limit, if that's even possible? As we know, some limits just don't exist. Well, this is where we bring in L'Hopital's rule. So L'Hopital's rule, call it a theorem, L'Hopital's rule says this: let f and g be functions that are differentiable on an open interval from A to B containing C, except that possibly C itself. So the functions don't have to be differentiable necessarily at C. Assume that g prime of x is not 0 for all x in the open interval from A to B. If the limit of f of x divided by g of x as x approaches C produces the indeterminate form is 0 divided by 0, then the limit of f of x divided by g of x as x approaches C is equal to the limit of f prime of x divided by g prime of x as x approaches C. And I'll go ahead and write down, note, this theorem also works for the indeterminate forms infinity over infinity, negative infinity over infinity, infinity over negative infinity, and negative infinity over negative infinity. So actually all of those forms can be tackled by L'Hopital's rule, and as well as one-sided limits. So the theorem is stated in terms of the indeterminate form 0 over 0, and it's stated as two-sided limit, but it works for these other indeterminate forms as well as one-sided limits. So how does that help us? Well, notice, if we come back to our previous example, the limit of e to the 2x minus 1 over x as x approaches 0, we already know from what we wrote above, we get 0 over 0, so that's an indeterminate form. It's indeterminate because what's really happening is the numerator we see is getting closer to 0. The denominator is also getting closer to 0. In a fraction, if the numerator gets close to 0, fractions have a tendency to be zero themselves. However, if the denominator is getting closer to zero, a fraction has a tendency to be infinity or negative infinity. So the numerator is trying to make this fraction small. Excuse me. The numerator is trying to make this fraction small. The denominator is trying to make the whole fraction large, and they're fighting against one another to see who's going to dominate. So this is why we have an indeterminate form. Anything could happen. The limit could be 0. The limit could be infinity or negative infinity. The limit may end up being 4, or the limit might not exist. And so we employ LHopital's rule. So by LHopital's rule, our limit is equal to the limit as x approaches 0 of the derivative of the numerator. Well, the derivative of e to the 2x is e to the 2x times 2. The derivative of 1, of course, is 0, divided by the derivative of the denominator. The derivative of x is simply 1. Now, this limit, e to the 2x times 2, that's a continuous function, and we know that we can calculate the limit of a continuous function by just plugging in the number, in this case 0. So we would get 2 times e to the 2 times 0. 2 times 0 is 0. E to the 0 is 1. 2 times 1 is 2. So we have used LHopital's rule to do exactly what we wanted to do. That is, we wanted to somehow eliminate this x, because that's the thing that's causing the fraction to have a 0 in the denominator as x gets closer to 0. And then we evaluate the limit to end up with our value. So we see that, in fact, the numerator doesn't really win because this is not 0. The denominator doesn't win because the limit is not infinity or negative infinity. They actually compromise, and they end up having the limit equal to 2. So this is an example and a little bit of motivation for LHopital's rule.